Yo, Eric, what are you up to there?
None of your business, Basil. Now scram, stop distracting me.
Excuse me? Okay, I'll be going then.
Ah, this doesn't make sense! Basil?
Eric, you sure there's nothing I can help you with?
I'm trying to prove the law of conservation of momentum experimentally, but I can't think of an experiment.
Well, I can help you with that. I present to you the Einstein decline.
Holy, but how does this magnificent contraption demonstrate anything?
When the blue marble rolls down the slide, it will collide with the green marble and launch it onto the pad below. We will use the law of conservation of energy to determine the momentum before the collision and the principles of projectile motion to find momentum after. Then we'll see if these values are close to each other. Let's see it in action.
Note that the blue marble momentarily stops immediately after the collision.
While we're performing the runs, we collected the data we'll use to calculate momentum. To start, we'll set momentum of the system before the collision equal to the momentum of the system after the collision, with each momentum variable equaling the total momentum of the blue and green marbles. As the velocity of the green ball before the collision is 0, p prime equals the momentum of the blue marble, which has an unknown velocity.
To find the blue marble's velocity and calculate momentum before the collision, we'll use the law of conservation of energy. As the change in energy of an isolated system is always 0, we can determine that the initial kinetic and gravitational potential energies, when added together, equal the sum of the final kinetic and gravitational potential energies. As the blue marble starts off with no velocity at the top of the ramp, we can say that its initial kinetic energy is 0, while final gravitational potential energy is equal to 0 as we are setting the bottom of the ramp as height 0. This provides us with a more simple equation in which GH equals 1/2 v squared.
As we know that g equals 9.81 meters per second squared and the height of the slide is 0.113 meters, we can substitute these values into the equation shown earlier to find the velocity of the blue marble immediately before the collision. We found this value to be 1.49 meters per second. To find momentum of the system before the collision, we multiplied this value by the mass of the blue marble to produce a momentum value of 0.00742 kilogram meters per second.
For momentum after the collision, we'll assume that the blue marble's movement is negligible, as it stops and only continues to move because of the slide's imperfect shape. Thus, momentum after the collision is equal to the green marble's momentum. To find it, we will use the principles of projectile motion. As the marble is not experiencing horizontal acceleration, its horizontal displacement is given by d equals vt. However, it is experiencing the vertical constant force of gravity downwards. Thus, its vertical displacement is given by d equals vt plus 1/2 at squared. As the ball does not have any initial vertical velocity, the equation simplifies to d equals 1/2 at squared.
We can then isolate t in this equation and solve for it, as we know that if we consider downward movement as being positive, that acceleration is 9.81 meters per second squared, and that the vertical distance between the bottom of the slide and the landing pad is 0.071 meters. Therefore, it takes 0.12 seconds for the green marble to hit the landing pad after the collision at the base of the slide.
We can substitute this time value into the equation for horizontal displacement and find horizontal velocity. We can then find the green marble's momentum after the collision. If we were to use the data found in the first trial, we can see that the horizontal displacement of the green marble is 0.162 meters, which provides us with a post-collision momentum value of 0.00676 kilograms meters per second.
To find the percent error of this momentum value, we can subtract the experimental momentum value, which is the experimentally determined green marble's momentum, from the predicted momentum value, which was calculated using the height of the slide, and divide this difference by the predicted momentum value to produce a percent error of 8.85% for the first trial.
Across 3 trials, the momentum after the collision ranged from 0.00668 to 0.00676 kilogram meters per second, with the percent error ranging from 8.85% to 9.97%.
Wait, but if the momentum values aren't all the same, doesn't that mean that the law of conservation of momentum isn't true?
Well, my child, it is likely that this test experienced some systematic errors. For example, the blue marble experienced friction while rolling, reducing its momentum immediately before the collision. Furthermore, if the blue marble collided with the green marble at a slight angle, not all of the blue marble's momentum would have been transferred to the green marble. Because these are unavoidable with our resources, we can say that since the post-collision momentum values were within 10% of the pre-collision momentum values, the law of conservation of momentum holds.
You figured it out. Now what should we do to celebrate?
I have an idea.